Okay, welcome to you all. As Istanbul University Observatory, we have started a new astrophysics talk series. So it will go on this time on each Monday. Our first speaker is Anirban Roy from Cornell University. He's currently a research associate in astrophysics and cosmology. So let me introduce him for a few words. He got his bachelor and master degrees from Burdwan University. He took his PhD from CISA on probing patchy reionization via CmB, LSS, and their cross-correlation. After that, he continued to research CmB and reionization era, LSS, etc. His study topics also include the SZ effect, CFR in high Z galaxies, line intensity mapping, etc. But beside all these professional studies, he also works for popularization of science among students and the public. So we appreciate him to accept our offer to give a talk here. So Dr. Roy, it's your turn now. You can start. Thank you. But you have to unmute yourself.
Okay, let me do it again. Okay, great. It happens always. So thank you very much for the kind introduction. I just want to say a few sentences in Turkish. Davetiniz için çok teşekkür ederim. İstanbul Üniversitesi'nde konuşma yapmak benim için bir zevktir. Umarım siz ve aileniz bu zorlu dönemde iyisinizdir. Unfortunately, my Turkish is not that great that I can continue the whole conversation in Turkish, but hopefully one day, why not? And so, as I said, that I'm working as a research associate at Cornell University. It is also a good time to acknowledge my collaborators because all the results I'll present today, it will be a product of working with these people. And so I was told that there will be master students. So first 20 or 25 minutes, I'll talk about general cosmology. And then if we are not very tired, I will try to explain some of the recent results that I'm currently working on. And also I'll talk that what are the future opportunities in front of us that are very interesting, at least according to me. So first, let me go. Okay. So just let me tell you first that what do we see? I know that I'm giving a talk at Istanbul University, Istanbul Observatory. So let me talk from the point of view of observations. So what do we see? This is a telescope named Polar Bear in the Atacama Desert, which is very hot and dry. So because there will be no rain, basically, so there will be no water vapor. And if I want to measure the temperature across the sky, I will see something like this, a homogeneous temperature. If I want to measure the temperature, it is a homogeneous temperature around 2.73 Kelvin. That's fine. But now let me give you a real life example. For example, today is 20 degrees centigrade and tomorrow is 40 degrees centigrade. I can feel it because my skin is kind of a thermometer that can understand that tomorrow is 40 degrees, which is much hotter. But what if today is 20 degrees centigrade and tomorrow is 20.001 degrees centigrade? Our skin is not that very good thermometer that can measure these differences. But what if I can understand the difference at the microkelvin order? I will see the sky with some temperature fluctuation. Some places I will see few microkelvin hotter than the average temperature, which I told that 2.73 Kelvin. And some places which are the bluish one is the colder compared to the mean temperature 2.73 Kelvin. And I have to be able to measure the temperature across the sky at the level of few microkelvin. That is the important point here. Now, what if I have more money, I have more funds, the technology is advanced, so I have that capability that I can measure the temperature at the level of 0.1 or 0.001 microkelvin. then what I will see not only measure the temperature of those photons along the different line of sight of the sky, I can also measure their polarization state. So we know that light is an electromagnetic wave, and it will have the polarization, linear polarization. We can actually understand the state of the polarization using a polarimeter of our telescope. I can now measure the direction or the polarization state, roughly speaking, of those photons. Now, this is what we observe. Now, let me go into details that why we see this temperature fluctuation across the sky. So I need to go back a little bit about the history of our universe. And a catch point is that I'll also compare with the history of Turkish national around the last 100 years. So let me first tell you the history of the universe. So what happened? Universe started from a hot and dense phase. We know it as a Big Bang. Time started from here. All those standard sentences we always heard in a cosmological in a talk of cosmology. And after that, universe went through an accelerated expansion that is known as inflation. And after that, we can consider after let's say a few minutes, because first elements will be produced, but that is a complex physics. I'll not focus in this talk. We can consider that universe is soup of elementary particles. What I mean by soup is that universe has main elementary particles like electron, proton, photon, and dark matter. Let's forget about other elementary particles such as neutrino and other exotic particles. Now, what do I mean by the soup of particles? Means that they share the common temperature because they were in thermal equilibrium. It is like a chicken soup, that if I take one spoon of soup, I cannot separate the spices and chicken and other stuff. I will basically take out all the soup. After that, when the temperature of the universe went through due to the expansion, the temperature become lower and lower. And when the thermal energy of the universe went below the binding energy of a hydrogen, then proton and electron combined together formed neutral hydrogen. And those photons, there were no photons that could scatter with those electrons because they combine the neutral hydrogen. From that phase, those photons became free. And that time we call this surface last scattering surface. After that, universe was kind of a boring phase. There are no more structures. There were only the dark matter that were acting gravitationally, and CmB photon, which is free. After around few 100 million years old, 500 or 600 depends. I'll talk in details. We have still uncertainty about that. What happened due to the gravitational collapse, first generation of stars and galaxies were formed, and they produce the ultraviolet high energy photon. And those photons actually ionize the intergalactic medium, and that is called the reionization epoch. And at this epoch, we can observe by 21 centimeter observation, Lyman alpha forest, and other probes. And at latter time, what we see at the present day, that a completely non-homogeneous universe with the structures like galaxies, cluster, and we can observe it with the large-scale structure surface and LSS. Now, I want to give, when I try to explain to people, I want to give kind of a history, and which I call a grandfather analogy, because this is the basic concept we use again and again during my talk. So for example, I have a grandfather who is 100 years old, and I am 28 years old. Now, if I were born in Turkey, I would, of course, experience the last 3 events in the history of Turkey, and I know about that. But I don't have information of Turkey around 1920 through 1952 or whatever. But I have my grandfather with me, so I can actually ask my grandfather, the grandfather, could you please tell me that what happened at that time? Tell me about these events. And grandfather can tell me about those events. But the interesting thing is that at latter time, the last 3 events, my grandfather has witnessed all those events, and I have also witnessed those events. So I can actually cross-talk with my grandfather. I can have a debate, or I can have a sharing of opinion with my grandfather, and we can try to understand those events better. Now, going back to the analogy of the CmB, that CmB is coming from the backlight when universe was 3.38 million years old, redshift 1100. And those lights are coming to us. And at later time, the large scale structure like stars and galaxies were formed. So those CmB photons are actually interacting with the later structure formed. And so those CmB photons are carrying information about the late time events. Now I have also more instruments I can do. I can do X-ray observation to understand the clusters. I have optical telescopes, and I can actually cross-talk with the CmB and ask CmB that, okay, what information you are giving it to me, and I can also see these structures, and I can actually compare these two observations or two conclusions by using the different probes. Today, I'll not talk about the early universe cosmology, but I'll probably mention one or two exciting top goals of the future CmB experiments. I'll talk mainly that how we can use the CmB for future experiments. Now, in this scenario, I can basically ask two questions: that how CmB can be used to understand the late time universe, like the grandfather analogy, that because the CmB photon has experience at late time events, so their energy, their polarization will be changed. And also, as the CmB photons are changing by the late time events, when I want to understand the early universe, these late time events can cause problems like creating like a foreground or distortion. I want to also know that how I can understand better by removing this late time event, the signature of late time events. So now going back to the first slide, that what we see basically, it is not that easy. If we have a Planck satellite and we have 9 frequencies, we observe the CmB in this way. Like, as you can understand, that it doesn't look like the picture what we already with which we are already familiar with. The reason is that at low frequency, we have galaxy and there is synchrotron emissions, and this is dominated by synchrotron. At high frequency, we have dust emission, and those dust emission actually contaminate the CmB. So what we do, we know the characteristic of the CmB, and by using some mathematical expression, I will say the mathematical algorithm, basically, which we call in scientific term component separation, what we get this clean picture. It is the best baby picture of the universe that is available to us by Planck satellite. What it is telling me that the red points are basically few microkelvin, few hundred microkelvins hotter than the mean temperature, and the blue spots are basically few microkelvin colder than the mean temperature. Now the question comes that what cosmologists always do, they want to understand the statistics of this map. We don't care anything. We want to apply mathematical formalism, and we want to understand the statistical properties, why these temperature fluctuations are happening like this. So one question we can ask, that what causes the temperature fluctuations like this? And the answer is quantum fluctuations and other late time events, as I said. Now, second thing, which is the difficult part, that how to model this temperature fluctuation. Okay, I can see some fluctuation. How I can mathematically understand this? And that we have a tool which is called spherical harmonics. Master students probably did when they solved the hydrogen atom problem. They had to use spherical harmonics Bessel functions. And last thing is that fine, we can model now by using some techniques, which I'm telling that spherical harmonics. Now, what does it tell us about? And that answer is a very big answer, which is that many things from the birth of the universe to present day. And now I will unfold that what we can learn from the CmB observations. So when we apply this statistics, we want to understand statistical estimators, we want to understand that how is the temperature fluctuations happening. I can see something like this. These are the error bars. What it is telling me, L small means the large scale. You can understand that 2 points in the sky are separated by a huge distance, basically huge angle. And L small means the smaller scales. L 180 is roughly around 1 degree, so that you can understand where the first peak arises. And on the y-axis, I am plotting the temperature fluctuations. So this is what my data is telling me. I have a Planck satellite. I observed the temperature along the different line of sight of the sky. I took the map. I cleaned that map, and then I calculated basically the variance, which is we call the power spectra in scientific term. And we calculated the power spectra, and I can see the data points are like this. Now, what these data points are telling me? Now, there are also theoretical cosmologists who are working on theory. They want to explain that if I consider the universe in a certain way, which we know today as lambda CDM cosmology, can we explain this data point? And what we see something like this, which is the blue solid curve. You can see that clearly it matches at least high L, which is the small scales. This blue curve, which is coming from a theoretical model, matches very well with the data points. On large scale, the error bars are larger, and we understand this why it is happening, which we call cosmic variance, because we don't have many modes. So the error bar is proportional to 1 by 12 plus 1. Anyway, I'm not going into the details. So we understand exactly how the error bars behaves at different scales. And now we have a model that matches with the theoretical data. Again, I can rephrase the same question, then okay, fine. Now what it is telling me in the end? It is telling me it is giving me some values of the parameters, because when I have parameters in that, when I have a theoretical model of the universe, I have some pre-parameters, which is we call the 6 parameters. These are, let me focus on the first 2 parameters, which is the baryon content of the universe, and second one is the cold dark matter content, basically matter and baryon. These are the 3 parameters of my model, and I can adjust these parameters to predict the data. So when I make an observation and I feed the model with the data, I can actually calculate these parameters, first 6 parameters. This is telling me that universe is actually very simple. We need to know only the value of the 6 parameters. That's the nice thing about this simple lambda CDM model. And we can measure these parameters less than 1% or something around 1% precision, and which basically tells us that 70% of our universe is consists of dark energy, all those standard cosmological interpretations. Now, the question is that, okay, fine, we know about the universe. We have a model to explain the universe. We have observations that confirm that model. What is the next? So I want to characterize the future experiments in 2 different set of categories. One is the CmB experiments. For example, PICO is the NASA funded, it is proposed to NASA. Lightbird is a Japanese satellite that is funded, probably is going to fly in 2027. Secret Prime and CmB is ground-based telescope. There is also another Indian-based proposal, which is called CmB Bharat. On the other hand, there are other which are not focused on the CmB science. For example, WFIRST, which now is the Roman Space Telescope, LSST or Vera Rubin Observatory, CRX, Euclid, SK, Square Kilometer. These are all. Now the thing is that, first of all, we want to understand better that what we can do with the CmB science. And the one important goal is that we want to understand, we want to detect the primordial gravitational wave, which is coming from the universe when it was billionth of a second, which is 10 to the power minus 32, around 10 to the power minus 32 second, depends on the inflationary model. We want to detect primordial gravitational wave. Now, why it is important? Because it will confirm many things. I know that in Istanbul University, people works on neutron star and the gravitational wave from black hole collisions. But this is also interesting because it is coming from the early universe. It will confirm that the inflation happened, and it will confirm that it is coming from the early universe. It will confirm that primordial gravitational wave exists, and we can measure the energy scale at that time. So it will basically tell us about the birth cry of the universe at that time, which is 10 to the power minus 32 seconds. That's why all those CmB experiments are actually setting their goal, they're funded to probe the primordial gravitational wave. On the other hand, we want to understand major thing that when reionization happened, when the first stars and galaxies formed and how they ionize the intergalactic medium. And also we want to understand dark energy at late time. We want to understand the formation and evolution of galaxies, and of course some astrophysical phenomena like the equation state of neutron star and gravitational wave. And I'm not an expert of that field, so I should not talk much about that. So anyway, now my journey starts from this point, that when we have these experiments, how we can understand better about several events, for example, reionization and cluster physics, with a focus on these experiments. And just to show that we have basically, I am part of these two collaborations, Feynman Observatory and CmB. I am somewhere in marked circle. Before COVID, we used to meet every 6 months and we used to discuss what will be the science goal, what is the status of algorithm and data pipeline. But now, unfortunately, we do it online, which is not that interesting or that encouraging when we used to meet with each other. Now, going into the details of the recent results, let me introduce with you one interesting event that has imprints on CmB, but also people are doing cluster physics with these signals, which is known as Sunyaev-Zel'dovich effect. So what happens that as CmB photons are traveling to me, it is also these photons are also interacting with the hot electron gas present in the galaxy cluster. What will happen? There will be inverse Compton effect. There will be energy transfer from the hot electrons to the CmB photons, because electrons are very high energetic and CmB photons have very less temperature. So there will be the frequency, because if there is no collision, it will be a black body spectrum. But if there is collision, the black body spectrum will be changed. And this will look something like this. So if I change the frequency, I will see a spot of the sky will change its intensity. So for example, if I see at low frequency, let me pause for a second. If I pause it at 150 gigahertz, my calculations tell me that I'll see a dark spot if there is a cluster. So I can detect it. But if I change the frequency, if I go to high frequency, I will see that that spot has become a bright spot. So let's say my observation is operating at frequency 150, and I am observing a CmB map. Whenever I see this black spot at 150 gigahertz, I can understand that these are actually the imprints, these are actually the signatures of galaxy clusters. So we take a CmB map and we have our own algorithm. I did not do, people in collaboration, they do it, and they run this algorithm over the CmB map pixel by pixel. And when they find these black spots, they detect that they claim that they have detected the galaxy clusters. Of course, they can do other physics with these. What is the mass of the clusters? What is the luminosity? They can infer all these parameters after doing this. Now, how it works according to these two equation, which we measure is y parameter, which is known as Compton y parameter. That is this that is the integral over the multiplication of number density of electrons along the line of sight and temperature, which is basically pressure. If I multiply with Kb, the Kb NET is basically the pressure. So it is basically measuring the y parameter is basically measuring the pressure along line of sight. And we know the optical depth, which we call that how many free electrons are there, which is basically the integrand over the number density of free electrons. Now, we want to measure this parameter by this observation, because this y parameter is related to the temperature fluctuation in the CmB sky. And when I measure the y parameter by doing some model, I can understand this electron density distribution, which is Ne, and the temperature of the cluster T by this equation. Because if Ne increases or T increases, then my y parameter will increase. That is direct measurable quantity. And optical depth is also same. Optical depth we cannot measure because we measure this pressure along the line of sight, which is the product of NETE, not only Ne. But optical depth has its own imprints on the CmB polarization, and from CmB polarization, we can actually measure this value of optical depth. And just to refresh everything, let me pause for a second. That what I'm telling, that from CMB, I have CMB photons are coming, then reionization happened. So what happened, those galaxies at reionization epoch, which is around the first billion or few hundred million years, they produced the ionized bubbles surrounded those ionizing sources that are galaxies. And those, as time passes, those ionized bubbles merge with each other and produced a ionized universe. Later time, when due to the gravitational infall, there are galaxy clusters, those CMB photons are also interacting with galaxy clusters. And finally, I am observing that distorted CMB photons. And my aim is to understand both the reionization epoch, somehow finding the signatures of reionization using that finally distorted photon, and also the signature of galaxy clusters. So now, as galaxy clusters are inhomogeneously distributed in the sky, what can I do? I can measure this Compton Y parameter along the different line of sight. Because if I have a cluster along one direction, if I look at another direction, if there is no cluster, I will not see any temperature fluctuation. Now, this Y parameter will be function of the electron density distribution and also the temperature. Now, if I measure this Y signal from reionization and cluster, it can be easily shown that Y signal from reionization is subdominant by the cluster. Cluster signal, cluster Y is very high, higher than the reionization one. The reason is that electrons in cluster temperature is much hotter than the reionization, because reionization will happen when around 10 to the power 4 Kelvin, when the cooling curve of the hydrogen. But whereas galaxy cluster electrons can go much higher temperature. But if we see the electron density distribution, it is kind of comparable with the ionized bubbles and the electron density distribution in the cluster. So tau is little bit, tau from reionization is around few times larger than the clusters, but kind of comparability, it depends on the modeling. Now, what if I cross-correlate these two things, tau Y? So what I mean by cross-correlation, that I have a map of optical depth and I have a map of Compton Y. And what if I correlate these two, which is known as the cross-correlation method, and then calculate the statistics of it, which is known as the power spectra? Can I understand better the characteristic of the galaxy cluster? And can I understand better in some way the ionized and the characteristics of ionized bubbles? However, just to let you know that there is no measurements of the size of the ionized bubbles or temperature of ionized bubbles in a direct way. What I mean by that, we know that reionization happened. We know that it ended at some point around between redshift 5 and 6. But how it happened, what are the sources of reionization, what are the morphology of reionization and topological information? We did it in the simulation, but there are no direct evidence so far. So that's why it is interesting to put some numbers, and that's where I was working last 1 year, just to know that from CmB observations, if I can dig out some numbers about the reionization epoch. And what we know about reionization, just to tell you that there are some data points. Again, those are not direct observations of reionization. There are some quasar data, which is quasar near-Jones data. There are some Lyman alpha data set, and what basically tells me that how much reionization happened at a particular redshift. These are some limits actually, but it doesn't tell me that how it when did it start and how did it end. So what we did, we actually took this data. We have also optical depth constraint from CmB, and then we tried to fit all of this data with the best fit reionization history. So when we feed this shaded region, this matches with the 1 sigma error bar of optical depth, and also matches with the limits from quasar near-Jones observations and Lyman alpha dataset. And blue solid line is the our reionization history, which we inferred from this variety of data set. That is also matches with the optical depth constant from the flank. Just having said that, I just want to tell that if you have any questions, feel free to interrupt me anytime. I'll be happy to answer those questions. And I think somebody has a question. Yeah.
I have a quick question.
Yeah, sure.
So I didn't get, I mean, I think I understand what you want to do, but I didn't understand fully how you do it in detail. So can you go back one slide?
Yeah, sure.
Or say, so you define these y and tau. I didn't fully get what this is. I mean, say,
okay. Yeah. Oh, this is actually confusing. Yeah, thanks for, yeah. So YY means when, because cosmologists always take the power spectra. So when I take the power spectra, so for example, let me go back quickly. Okay. Okay, so you can see this is the CLTT. It is the power spectra of temperature, which we write as CLTT. If we take power spectra of something, we always represent it at CLYY or CL tau. So when we take the statistics, we write it as CLTT. But I mention only the TT means basically in our nomenclature that it's like basically the power spectra of that signal. For example, here I am taking the power spectra of temperature. There I am taking the power spectra of Compton Y parameter.
okay, I
now
see.
Let me go back. Yeah. So what I mean by YY signal is the power spectra of Compton Y, which is CLYY, is subdominant by CLYY of cluster. On the other hand, the CL tau from ionization is larger than the CL tau from clusters.
Okay, I get it. So these are just not these quantities that you showed, but the power spectra.
Exactly.
Thanks a lot.
Okay, no problem. It's my pleasure. Yeah, feel free to ask any questions. There is always a quote that there is no bad question, only bad answers can be. So it will be on my blame. And anyway, so yeah. Okay. So this is my final scenario that I have a now best fit ionization history that matches with variety of data set, also that matches with the 1 sigma error bar of tau. And I was a exchange student at Cambridge University for a few months, and I worked on this project there, and they have this best simulation available so far that is called the radiative transfer simulation. Why I'm mentioning this, because these are very computationally expensive. So to store the data, to run the whole simulation, it takes basically few weeks. And then if you have some problem, you need to go back and checking. So they claim that they have the best available simulation so far that agrees with a variety of data sets. Now, what I did that I want to understand that ionization imprints on the CmB. And for that, I need a large box. As I said, that radiative transfer is very computationally expensive, and their limit is around 160 megaparsec. They can generate ionization field and halos density field at that scale. So, but I am coming from the CmB background, but to understand the imprints on the CmB, I need at least 1 gigaparsec, the box which is around 1 gigaparsec size. So what I did, I came out with some techniques that I will not run your radiative transfer simulation, but I will create my own simulation that based on which is called excursion set principle, excursion set formalism. And I will calibrate my simulation, excursion set simulation with radiative transfer simulation, and then I will run my own excursion set formalism, not using the radiative transfer simulation. So this is the result kind of which shows on the density plus halos. So what I'm showing on the left panel, that density fluctuation, which is the dark matter density. The yellow spots are basically the overdense region. It means that this is the density is higher than the mean density. And the red spots are basically the underdense region. And then these black spots are basically the halos, location of halos. Of course, where will be the denser region, there will be the stars and galaxies will form there. Basically, I call it halos in general way. So that's why you cannot see actually the yellow spots. It is covered by the halos, because halos are sitting there. The minimum mass of the halo is 10 to the power 9. So basically the galaxies can sit there. Now I am taking some assumption that if it has to reorganize the universe in such a way, how it will reorganize. And that is this movie that I'm showing, that the white spots are basically the neutral region and blue spots are the ionized region. So it will, based on this density field and based on this halo location, it will ionize the universe in such a way. Now coming back to the point that what we want to do now, we have now simulation to understand somehow to model this reionization epoch, which is very complex. So what we want to do, we want to make a map of optical depth. Like we make a map of temperature, we make a map of polarization, or map of anything. Astrophysicists do map of X-ray map of galaxy clusters or whatever. We want to make a map of optical depth. Now, why optical depth is interesting? Let me just tell you a bit. So one success of the Planck satellite is that they measured CmB lensing, which I did not talk about, but what the main idea is, by observing CmB lensing, they make the map of the projected matter density. So the left panel showing the matter density of the universe inferred from CmB lensing, the projected matter. So it is kind of acting like the matter template of the universe, because it is integrated. Same thing we want to do, we want to make the map of optical depth, because optical depth will carry the information about free electrons. So I have one map which is carrying the information about the matter density of the universe. I have another map that is carrying the information about the free electrons. And now it will be interesting to cross-correlate to check that how electrons are related with the matter and all those interesting stuff. And also this optical depth, as I said, again, just to highlight the point that it will carry information from reionization, from clusters, from diffuse sources. And this has not been done so far. So again, to use some toy model, just to understand that if we can measure some parameters, this is the probably slide based on the mathematical equation. What we want to do, that we want to understand the statistics of ionized bubbles before they march with each other and ionize the universe. So from simulation, we have seen that you can roughly model the spread of the ionized bubbles according to a log normal distribution, which has basically two parameters. One is the R bar, which is the characteristic scale, which is basically what is the probability that maximum bubbles I can get with a certain radius, which is R bar. And what is the spread of that log normal distribution? You can consider it as a Gaussian distribution. What is the mean value or something like that? What is the spread of distribution? Now, these are the two free parameters of this model. That's why I have written it as a toy model. And so the question is that, okay, if we have observation, if we make a tau map, and if we have other observations, can we measure these parameters? So what we did last year, we took a Planck map of CmB. We reconstruct a tau map from here, which is very noisy because the sensitivity is not that good. We have Y map, and we cross-correlate these two. Now, coming back to your question, now I am writing, because it is cross-correlation, I am writing as CL tau Y. So tau cross Y. And what we see that there is some signal based on from L range, let's say 250 to 800. So there is some non-zero signal, but that signal is not telling me many things because it is kind of consistent with 0. Now, this is the first measurement we have done. There were no measurement from CmB, and this paper came out with a message that from CmB we can do also more things about reionization. Of course, when SKA square kilometer array will operate, there will be much more information, but it is just to tell that from CmB we can use also complementary sciences that can be cross-checked with SKA. Now the question is that can we estimate some parameters of reionization? And this right constant plot is actually showing the 2 sigma upper limit on the value of RB, which is the radius of the ionized bubbles. What is the spread? And most important thing is that temperature, log temperature, which is basically telling me 10 to the Q into 10 to the power 5 Kelvin, which I'm basically highlighting with a red circle. Now the problem is that what other complementary observations tell us that it will be few into 10 to the power 4. So we are getting actually 1 order of magnitude larger, and there is no explanation because there are not many different set of observations. But we think that because the data is so noisy, though it is a fast constant from CMB, but we expect this data will improve significantly with future CMB experiments. And if we cross-check, we believe that we can measure this temperature at the 10 to the power 4, few into 10 to the power 4 Kelvin. And that will be an interesting error to check, because why I'm telling interesting, the reason is that when I'm telling about other complementary probes, those are basically coming from the quasars and Lyman alpha. There at high redshift, there are very few quasars. So I am basically having few quasars. I am modeling those quasars. I'm assuming something, and then I'm estimating the temperature. But it doesn't reflect the global property of ionization. If I have a 10 quasars at Z greater than 6, this temperature depends on those sample, which we call that sample variance. But on the other hand, CMB just full sky map, or at least 70% of the sky. So the global property of ionization is imprinted in the CMB sky. So we expect that if it is the case, it will be a very interesting probe to check, because, for example, if from quasar data we get few into 10 to the power 4, let's say 10 to the power 4 Kelvin, and if we get 5 into 10 to the power 4, now why we are expecting more hotter electrons during the ionization, we can try to understand why this is happening. There are some exotic physics like dark matter annihilation and other things. We can actually try to focus on those shaded areas. But I also promised that to talk about few billion years to present day. So let me talk the last 2 things before I end up, that what we know about the clusters, because clusters will also make imprints on those CMB map. The problem, as I said at the beginning, CMB is like grandfather, so it is actually going through all those events. So I have to ask my grandfather a correct question to get the correct answer. And as my grandfather is old enough, so it may lose. He may lose his memory a bit, so we need to dig out some information in a clever way. Same thing here. Now I want to ask that, okay, let's forget about the ionization. What we can know about the cluster. Now this I'm showing that when we define the cluster, we define the radius, which is R2500, 2500, which means that the cluster density enclosed in this radius is 2500 times larger than the mean critical density of the universe, which is rho c. When I tell that R500, it means that the cluster density is 500 times more than the critical density, and 200 is so on. So the radius will increase because the core is basically high dense region, and then the density falls, like NFW, Navarro-Frank-White profiles and other profiles also. So we are interested to know the 3-4 things, which is the statistical properties, density, pressure, temperature, and the basic thing we want to understand that what about the baryons in this cluster? Because the thing is that there is a unsolved problem, which is that missing baryon problem, which basically tells us that we don't see the baryons in galaxies that we expect from the cosmology. So if cosmology tells me that there will be 0.22 with some arbitrary unit, I get probably 0.12. So why there are not enough baryons present in the clusters? So now the question I'm framing, that can we measure some properties of the galaxy clusters or galaxies to some extent? Now this is a very busy plot, so let me explain slowly. So what I am doing is I'm measuring the tau power spectra of galaxy of the CMB field that takes into account the contribution from galaxy clusters. And I am changing the value of M min, which is basically telling that when I am putting the threshold mass limit on the galaxy cluster. So for example, my M min is 10 to the power 11, it means I'm taking into account some galaxy clusters. If my M min is 10 to the power 13, it means I'm taking the kind of galaxy clusters that are heavier than 10 to the power 13. If I limit it from 10 to the power 9 to 10 to the power 11, I will take account only the galaxies, because galaxies mass range fall in this galaxies mass usually falls in this mass range. Now I am forecasting that if I have a CMB experiment with some specification, for technicality I am not mentioning those, but just to mention, if I have a CMB S4-like experiment, can we measure this? And if we can measure this, what will be the signal to noise ratio of these experiments? And it shows that if we have if we observe 70% of the sky, around 4 sigma, we can measure this signal. Now what I am doing, that okay, fine. Now what if I cross-correlate with galaxy samples? That will be probed by LSST-like samples, which is Vera Rubin. So if I cross-correlate this tau map electron density, which is basically electron density distribution of free electrons along the different line of sight, if I cross-correlate with galaxies, can we measure this signal? And it shows that as we can measure the galaxy samples very well from Vera Rubin, which is VRO, it was LSST before, so VRO-like experiments, we can measure this signal more than 10 sigma, and that will be an interesting probe to see. Same thing, we did it for tau y, and it says also that we can measure this signal based on, of course, based on that how I am selecting the mass range, because LSST will have a different mass resolution. But overall, these plots are telling me that I can measure these signals more than 5 sigma. That is a good thing. And as these are independent probes, I can gather information from these independent probes, and I can try to constant some parameters. And this last slide, this slide on this topic, I'm showing that when I'm combining the information from all these parameters, just forget about the mathematical notation. The first column is actually telling me how I can constant the pressure, the density profile, which is rho 0. And this is a very busy plot, and I apologize for that. A lot of information is here. So what this left panel is telling me that I can constant the pressure and density profile of the clusters. And the interesting thing is that when I measure the density profile in the clusters, I can translate it to the which is we call the gas mass fraction, that how much gas is there. Interestingly, we see that usually kind of find all the baryons in the clusters. Now people can ask that, okay, but you are talking about the missing baryon problem, you don't see. Yes, the thing is that the catch is that we don't see in the X-ray observations, and we don't know why we see that less baryons. But there are some PL papers that combine different probes, and they came to the same conclusion that there are baryons present in the halos, but they are not, their temperature is not high enough, or they did not cool also that much, so that they can form stars, and those stars will illuminate light. So that's why we don't see it in X-ray or optical, but they are present in there. They're like a ghost sitting there. But for CMB, it is a different case, because even they are sitting like a ghost, they will scatter. Those electrons or baryons will basically interact with the CMB photons. So they have imprints in the CMB, but we don't see its imprints in X-ray or optical observations. So our estimate says that we can calculate, we can constant this gas mass fraction at 7 to 10%, based on some assumptions like what profile I'm considering, what density profile and pressure profile I'm considering. Now, in last 2 slides, I want to talk about another interesting thing that I have started working on during my postdoc. I did not work on it before. So now, which is called line intensity mapping. So what happens that galaxies also include some molecular and atomic elements, for example, carbon, oxygen, and carbon monoxide, and other nitrogen and other elements. And when the galaxies will produce high energy photon, they will actually there will be ionization. So for example, O3 means doubly ionized oxygen atom, and there will be a transition there. And those emissions will come to us with a redshifted factor, which is 1 plus Z. So basically, if I know the frequency, rest frame frequency of the transition of doubly ionized oxygen, I can observe it at a particular frequency. And by comparing this, I can understand that at which redshift those galaxies are sitting. Now, if I have many different atomic lines I can observe, I can actually understand the whole evolution of the galaxies or whole evolution of the universe, because now I don't have only CMB, I have also only different lines in my hand, and I can observe that. So I am now working on modeling, because this CCAT prime telescope, which is going to be a pioneer telescope for line intensity mapping, but it's a very small collaboration. So I'm working on pipeline developing for how we can analyze this data. If we analyze the data, how we can interpret those data, because the problem is from CMB, we are kind of experienced. We have 3rd generation, we are going towards 4th generation experiment. So we have idea how to separate those signals, how to do science with this. But line intensity mapping, we are going towards the 1st generation experiment. So we don't have practical information how to handle data and all these things. So I am working on simulation pipeline, and also to working on analysis tools, how to do this. I'll just show one plot. So the idea is that we want to first understand the halos, and then we want to understand the star formation rate. And that is the uncertain part of it, because there are a lot of physics there, and which we also, particularly I also don't understand, because I am not from that, I'm not coming from that background. But we have some simple models, we can do that. And when we know that star formation, we can understand that how luminous those different lines, for example, oxygen 3 or carbon 2, these lines will, what will be the intensity of these lines. And when we know intensity, then from that part, we are kind of expert, because we did it with the CMB. We know if we have an intensity map, we can take the power spectra, we can make the map, we can analyze those power spectra. But these first three steps are kind of crucial, because there is a huge uncertainty of modeling of star formation history in galaxies. And the final thing is that it has a lot of potential. Of course, I don't have time to show. One can probably talk hours after hours about details of this physics, but this is a simulation package which I'm working on, which is called LIMPy, line intensity mapping in Python. And this basically showing me that the left simulation animation is showing me that, as you can see, that there are different intensities at different different spatial points. Now I am changing the beam size of my instrument. So when I'm starting from the 30 arc second, and then I'm increasing it to 240. So when I go to 240, it means I have very bigger beam size. So it cannot resolve the small halos or small intensity points. So it will kind of blur the whole map. Now we know what will be the beam size of an experiment. The thing is that we will observe one of this map, and from that map we'll take the power spectra, which I'm showing in the middle panel, and then we'll do the cosmology. Just to give an overview that there is source of reionization, there are a lot of ISM physics. For example, one thing, again, I'm not an expert, but one crucial thing there is that star formation rate decreases below, peaks around redshift 2, and then it decreases, and we clearly don't understand what happens. So if we do tomography, if we can scan the universe or scan the galaxies at different redshift and map the star formation history at let's say z is equal to 2, z is equal to 3, z is equal to 4, we can kind of understand the evolution, and that is the aim. We are not still sure that how well we can do it, because there is a huge uncertainty in the model, but at least it will be a pioneer, it will be a new window, not only for the cosmology, but also astrophysics. Now I came to the end, and usually when I give a talk, I try to present the talk in a philosophical with a happy note. So I will end up with a little story, because as I am at Cornell, there Professor Carl Sagan, who had a huge impact on me. Unfortunately, he died when I was born in the same year, I guess, 1993. So in that building, there is Carl Sagan Institute. They work on finding exoplanets and characterization of planets, their atmosphere. So probably, I am sure that probably most of you know this story, but just to end this talk with a positive note, let me tell you the story. So the Voyager 1 satellite, it was launched much before, around, I think, 1970s. And the main aim of this satellite was to go further beyond our Earth and take pictures of other planets, and it will go to the outer side of the planet, outer side of solar system. And of course, Carl Sagan was very famous at that time. He had his own lobby. So originally this Voyager 1 satellite was supposed to work for only 10 to 15 years, but it actually worked for 44 years in the end, and it was probably last year or in 2020 it stopped working. Anyway, so in 1980s, in like 1989 or something like that, Carl Sagan was lobbying for doing one thing, that is that, okay, it is kind of going, it will not be that much operational, but what if this Voyager 1 telescope is going far from our Earth? What if we just move it back and take the picture of our Earth? And we do it. And of course, if you are the PI of this big telescope, you cannot press a button and you cannot just do it like we do selfie of our phone. So he needs to do lobby for, he did lobbying for this, and finally the PI and the whole committee agreed. And he told that it will not be a probably great scientific image, but it will be probably a great picture that will tell us about our existence, our philosophical thoughts, what we are doing. And I personally find that it will be interesting to tell his code as he wrote, because staying in this present political economic condition of the world, I think this picture still carries its own value. And I just wanted to tell his code, which is still inspire most of us. So just tell that he named this dot is pale blue dot, and just to tell that it is kind of a less than a pixel. Now we use 10 to the power 6 megapixel phone, megapixel phone, which is 10 to the power 6 pixel, but that time it was less than a pixel. And he told that, look at that dot, that's here, that's home, that's us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives. The aggregate of our joy and suffering, thousands of confident religions, ideologies, and economic doctrines, every hunter and forager, every hero and coward, every creator and destroyer of civilization, every king and peasant, every young couple in love, every mother and father, hopeful child, inventor and explorer, every teacher of morals, every corrupt politician, every superstar, every supreme leader, every saint and sinner in the history of species lived there on a mote of dust suspended in a sunbeam. So just to summarize that, probably our contribution in science is like a drop in a huge ocean, but I think it is good to summarize this thing. And my last slide is that I will end up with, just a second, with two poems that particularly I am inspired of. One is by Najim Hikmet and one is by Robert Frost, both actually kind of telling same thing, also different things to some extent. And I think, as I am virtually present in Istanbul University in the campus of Istanbul University, I think it would be nice to end up with these two beautifully written poems Unfortunately, I read it in English, so I did not paste it, but I know the name of the poem in English is On Living by Najim Hikmet, and it is also Robert Frost. They both are kind of telling the same thing. And I will end up here. Thank you very much for your attention. And if you have any questions, even after the talk, feel free to write to me. I'll be more than happy to talk about anything. Thank you.
Thank you, Dr. Roy. We appreciate you with this very instructive, informative talk and with very interesting research by you. So I would like to ask the audience if there is any question or not. So if there is questions, please ask to Dr. Roy.
Okay, I have a quick question. So,
Yeah, sure.
And first of all, it was a very nice talk, very instructive.
Thank you.
So, I mean, you try to disentangle two very different signals coming from different times. And so, there's a lot going on there. And so what I wonder is, do we fully understand, I mean, in particular, this rests on this physics of reionization. And so you mentioned one process, inverse Compton scattering. I just don't know enough about this. I mean, is this a model, or is this basically all, and we can neglect anything else that could happen? And this is really kind of all we need to do and to disentangle these two different, well, as I said, very different signals.
Okay, so yeah, let me show quickly one interesting product. Actually, I showed this slides maybe last time when I was in Istanbul University, so maybe 2018, so I did not show it, I put it in backup. So what happens that for WMAP, like satellite, they saw it something like this, which is the CmB in a particular patch of the sky, and it sees the fluctuation like this. Now, if Planck sees, because it has better resolution and better sensitivity, as you can see, this is the kind of same patch, but with better resolution, we can see very clear. And if we, oh, sorry, I just showed, okay. So now the question is that we need to find the clusters here. That is the aim of to a cosmologist. And what we find kind of something like this. So what this blue circle is telling, it's the primordial CmB fluctuation that I expect, like it happened in the early time. These yellow spots, which you can see kind of black spots, these are galaxy clusters. Because I can have an algorithm and I can understand these clusters. I can detect this cluster on the same map. And then you can see this bright spot. These are basically the starburst galaxies or active galactic nuclei. So I have a CmB map. I have basically imprints of all these things. Now I understand different processes. I know how they will make its own signature. And then I descending all these things. Now you are talking about reionization. We don't expect that in Compton map reionization, because reionization signal is 10 to the power 3 times lower. So we don't expect that it will be a problem with this. But it's a very good question, because it's a very hard task to basically detect the clusters. And we have actually detect from SPT many clusters with using this technique. So as you can see, so that actually works in the reality. So.
Oh, it seems you're busy. So many different.
Yeah. So these are basically panel, and you can see the bright spots are in the center of every panel is a cluster. So they detected more than 500, and for CMBS full like experiment, we expect more than few tens of 10,000. More than 10,000 clusters. So now we want to do cosmology with this cluster. We want to understand the mass and all those physics. We are talking about that.
Well, okay, thanks a lot.
Welcome.
I think we have one more question.
Yeah, sure.
Is that me? Is that
Yes,
me?
it was you, Sholan. Yes.
Okay. Okay. Hello.
Hello. Hi. Thank you.
Hi. My question will be just a little bit quick, I think, because I'm not quite an expert on these type of extragalactic CMB issues and things like that. But in the very last few slides, you showed tracers, new tracers. You're using lines, molecular and emission
Yeah.
lines for tracers, right?
Yes, yes.
And where are they? Here. Yeah, this is the one. Okay, you're going to use tracers to basically you're going to use line luminosities, convert those to intensity, and do spatial mapping in a way. Do I understand that correctly?
Yes, exactly. That's what. So from this, we want to get this map that is on the left panel. We want to make a map, and then we want to model those.
Yeah, that's
processes.
what you're trying to do. But what I want to understand here is that, okay, and other type of stuff you're doing, you're looking into more continuum type of emission or more continuum modification and so forth, as I see it. Here you're looking into lines. Now, looking into lines is a little complicated, I think, because line emission has a lot to do with the plasma itself and the plasmatic environment. Okay, and you're going to take that and what I'm trying to think, this is not something uniform actually in itself. So this is not going to give you a uniform actually intensity distribution, because this is going to also depend a lot on the plasma's own characteristics. Therefore, though, I mean, these lines seem to be cold lines and more sort of optical stuff, oxygen 3, and you have carbon oxygen here, as I see, some molecular stuff. But then I'm thinking about your efficiency in the sense, and your derivation of all this. I'm thinking that you're going to have a lot in here. You should have some sort of this is more like a question and a comment and things, you know, that popped into my mind.
Feel free to make comments also. I'll be here.
Okay,
happy
so
to hear
I'm
comments.
thinking that you're going to have a lot of inefficiency in this map. You could have a lot of inefficiency in the fact, not just the rate of intensity, because of the you might get something proper if the environmental conditions in the plasma, I mean, because you want to take these lines wherever they're emitted, you're going to, this is going to give you a mapping, but then there could be the environment where you have the line emission could be damped for other reasons within the same environment, or the intensities actually vary because of the plasma itself, but not the way it traverses through the universe. Do you understand what I'm trying to say?
Yes.
So
I completely.
You're going to have problems sampling actually the physics and the basic the basic idea of your mapping technique. Do you understand?
Yes.
Okay.
Yes, I guess I got your point. So okay,
I don't know,
okay, let me just respond.
I'm thinking a lot of the times, because all these things are spread out so much, you will have, my thinking is that a lot of collisional problems. You need collisional plasmas and to get these line emissions out, and a lot of the times and it could be even time dependent, that you may not have collisional plasma in the sense, and that your line luminosities could even be time varying, even in back tracing back even in history of universe, you know. But this is vague stuff. So I think you have here, it's interesting, but you have here a lot of things you need to consider in your map, and that you should, the plasma conditions themselves and time dependency of the plasma environment itself, rather than just the emission we receive here in that sort of speech. This is what I thought. I mean, that it's more of a comment. And have you ever, I mean, perhaps a question to you, have you considered biases or physical conditional biases that will inhibit your or affect your result in that manner. But this is something way vague, but this is what I sort of popped into my mind and I thought I shared.
No problem. That's a wonderful comment, and we studied this in detail. I did not do it, but in our Secret Prime science paper, we clearly mentioned this in one section. We clearly address this issue. So the thing is that the main thing is that, as you said, that there should be atomic transition, and that's why it needs the plasma should have a temperature that can basically knock out the electron. That's the main thing. Now we don't understand. First difficulty is that if I want to understand if a galaxy is a mass of 10 to the power 10, what will be the content of the carbon atom or oxygen atom? That is the thing we don't understand clearly. The way they model it, they observe ALMA, the galaxies by ALMA-like experiment, and they try to make some luminosity versus this line intensity as just some scattered data. It's a scattered data, as you said. You cannot, there will be bias, so they match the scattered data with the power law. So they know it's a very hard to model, but trying to somehow match with the observation with the data. So it's a very good question or comment, whatever I say. The reason is that now you can ask that who said you that it will be a power law? Sorry, it will be a power law, like, because it is not backed by any physical formalism. It is not backed by anything. The thing is that we don't know, and that's why these line intensity mappings experiments are interesting, because you first observing the intensity map, they want to basically ask this question, like what are the physical things are responsible for. One example, we want to understand that how star formation history, which is basically related to the plasma content of a galaxy, there are called AGN feedback. Basically, some quasars they emit emit the energy outside. We don't know, because so they want to measure all these things, also kind of marginalizing this all the parameters. But we know this problem exists, and this is not very clear statement that okay, we measure line intensity mapping and with 2% accuracy we can measure the star formation rate. No, if I did not show it here, but if I even show the different power spectra plots, there will be probably, I mean, 2 order of magnitude same thing I'm doing, but there will be different lines. It will be shaded lines with a huge error. But the reason is that this shaded error bars come from the astrophysical uncertainty, which you are basically mentioning. So there is an uncertainty which we know, but as these are first generation experiments, we want to first have the line intensity map. We want to measure it, and then we want to do more analysis and try to see that, because then the thing is that the importance of these questions are that then we can, after having the first measurement, we can actually ask this question that what kind of experiments we need to understand this detailed physics, because my experimental sensitivity should increase to understand this physics clearly. So yeah, this is a very good question, and we have thought about it, but there is no unique solution.
Yeah, that's what I thought. There is no unique solution actually. So one need to really be careful. You need a lot of interpretation while you're doing that.
That's why we are assuming 10 models. So there are 10 authors who wrote different papers based on different assumptions, and we are considering simulations also. Those simulations also don't agree with each other. So we are basically showing the results. We are showing that these are model independent things.
Okay, thanks for the details.
Actually, we are over our time already, but I think we can have a quick last question by Kaiser. We listen you.
All right. Oh, okay. Hi, Dr. Royce. Thank you so much. Right. Is my voice, can we hear? I don't know.
Yes, I can hear you clearly.
Okay. Oh, right. Thank you. It's a really interesting talk. Can I ask like more a physical question? Actually, like you mentioned it, how I think they asked before, like tau y, and also there's a graph there is different kind of like intensity kind of graphic of tau y j also. So like right.
Okay. Oh, I think you are talking about this plot, right? This plot or
no? There's like there's a
okay,
gray
another plot.
and
Oh, okay, yeah, this one, right?
right, something like that. Like right, like right hand side. There's a
Okay.
yeah. So it is like a partial interaction of them, or
Sorry, I actually did not understand. Could you please repeat
like
your question again?
right. I'm so sorry. The tau y tau those the particle interactions, or maybe I'm not
Oh,
familiar with.
no. That is not related to particle physics at all. So this is tau y means optical depth and y means Compton. So if I go back, this okay here. So tau is the quantity that imprints on CmB, which is the pressure along the line of sight. So if I have a cluster pressure and everything, I can understand this with the measuring the y parameter. And tau is the optical depth, which is basically taking into account the electron density around the line of sight. So they are nothing related to like particle interaction, the subatomic particles. These are like macro physics.
Yeah. Okay. So thank you so much. That's
Welcome.
Okay, thanks to Dr. Roy again, and for the audience being here. This was our first episode of the talk series organized by Istanbul University Observatory. So it will be go on this time on each Monday. So the next speaker will be announced later on again. So thanks to you all. Bye for now.
Bye bye. Stay safe.
Bye.
Thanks.